at this time. So without much delay, let me introduce the resource person of the day, Dr. Mandya Ravishankar sir. He is currently working as Associate Professor in the Department of Mechanical Engineering, IIT Tirupati. So coming to this educational qualification, he has completed his BTech from Sri Venkateswara University, Tirupati, and completed his MTech and PhD from IIT Kanpur. His current area of interest are nano and micro manufacturing, sustainable manufacturing, precision 3D printing, online monitoring, biomanufacturing, coating, tribology, etc. He is, to his credit, he has 60 international reputed journals, 10 international conferences, 6 patents, 2 edited books, and more than 10 book chapters. So as far as the funding is concerned, he has a lot of funding from BARC, DST, DRO, etc. And he is currently involved in review of 10 topmost international journals, starting from the Springer, elsewhere, etc. So coming to the awards, he has received awards from the Institute of Engineers India Young Engineer Award in the year 2015. Then finalist of Indian National Academy of Engineering Award in the year 2014. He also received a Best Paper Award 3 times in national and international conferences. So with this, I'll invite Mr. Dr. Ravishankar sir for the session. Over to you, sir.
Yeah, thank you. And I'm going to start.
Arun sir, please stop sharing from our end.
I think you have to, somebody is already shared. So
now we have canceled.
Can you able to see?
Yes, sir.
Yeah, full screen mode, can you able to see?
Yeah, now it is okay. Fine, sir.
Yeah, thank you. So whatever happened, actually, those are all from my side, actually. So for which Shanmugesh has apologized, but really the person who has to apologize is me, because we are also in a big busy schedules. Okay, so when I was accepting that at the time, I don't know what happened. Later we came to know that we have to conduct online written examination for PhD and MS, MTech selections and other things. So currently I am heading the department. So as per because our HOD is out of station, so I am being a chairman. I have to be there for all the things. Okay. So by the time examination conducted, it is 1:45. So it slipped from my mind. I just went to the food. When I was taken my first roti into the plate, I got a call from Shanmugesh. Then as soon as I just saw the time, so anyhow, then I ran away and came. By the time there was a net failure. So because of something, I don't know. Okay, so all this happened. So hope everything happens for the good. That's all. So I will try to explain you about one of the research area that we work is smart manufacturing. What I would like to say is, if you know the manufacturing in and out, then only you can make this particular process a smart manufacturing. Okay, smart. So to convert, no, it's a, for example, if you know the physics, so coding is in a particular language. Okay, so that is what. Oh, smart manufacturing is extension of what you know. Once you have, for example, abrasive flow finishing, if I know in and out, then I can make it as a smart. So how we are going to convert it, that you will see. Before that, what you are going to see is just a glimpse of what we do at IIT Gauhati and IIT Tirupati. As you know, that I worked at IIT Gauhati nearly 7 years. Then I moved to IIT Tirupati 2019. So where we work extensively into 5 areas. One is micro machining and nano finishing group, sustainable manufacturing group, bio nanomaterials and manufacturing, additive manufacturing group, and smart manufacturing group. So currently what I'm going to talk, nothing in this world is particular group or particular group. So everything is interdependent. For example, today's what I'm going to talk is the first one and the fifth one combination of these things. If you don't know fully the science of the first one, you cannot go for the last one. Okay. So what I'm going to talk first is just to give you the glimpse of what we do at IIT Tirupati and Gauhati. Then I will start with the physics and mechanism of abrasive flow finishing, which is a part of nano finishing group. Then how we have converted a conventional machine into a smart machine, that I will just tell you. So the first group, that micro machining and nano finishing group. So we work into extensively on micro machining of drug eluting stents, micro machining of lot of things like nuclear applications, microfluidics, automobile applications, and we also do laser cladding systems. So laser cladding system is again one way of additive manufacturing, because you are going to coat some microns or thickness on the surface. Okay, so you can do this coating by multiple means. Being a mechanical engineer, normally we try to do by lasers. However, there are better processes such as physical vapor deposition, chemical vapor deposition, and HOAF, high velocity oxyfuel coatings, and many varieties are there. So if you see the another variety of finishing process that we work is the magnetoreligical finishing. These type of finishing operations are mostly used for lens polishing applications. For example, if you see how the lens is polished there, just I would like to tell you how this is going to polish and other things. Once the fluid is there, so once the fluid is there, it is randomly oriented. Whenever there is a magnetic field applies, for example, if I stop this, okay, so the magnetic field will come. You see the red lines, this magnetic field comes. Now, once a magnetic field comes, what is happening? This is called magnetic field, application of magnetic field by the virtue of electromagnets. So these are called CIP particles, carbonyl iron particles, and these are abrasive particles, whatever. So by this polishing called as a smart polishing. For example, if you take the grinding process, a specification of a grinding wheel, how do you specify? Type of abrasives, size of abrasives, grade of a wheel, structure of a wheel, bonding material. These are the 5 varieties. Grade of a wheel means how firmly the abrasive particle is held by the bonding material. So at a particular instant, you can order soft grade, hard grade, or medium grade, or whatever. But in this case, depend on the magnetic field intensity. Normally, magnetic field intensity will be represented by B. Depend on the magnetic field intensity, this chain strength will be decides basically. So whether if you want to soft grade, you can go for low value. Okay. So if you want hard grade, you have to go for high value, like 1 Tesla and above. Okay. So what will happen? So that mechanism I would like to show here. So if you see, these are all small particles, which are you are seeing at the bottom. These are all CIP particles. CIP stands for carbonyl iron particles. And there is no magnetic field here. When the magnetic field is in absence, what will happen? All are randomly oriented. When the magnetic field is applied, okay, you see these chains are forming, and in between the abrasives are entrapped. You can see the abrasives are entrapped. Now, if you are going to provide a relative motion, what will happen is this will shear the material in a controlled manner. Now, the question is how firmly these abrasive particles are held is the biggest question. That is what the smartness is. That is, the smartness is depend on the magnetic field intensity, how much you are applying. This will decide the holding ability. As I said, the grade will change. If I am applying 0.25 Tesla, soft grade, that means that loosely bonded. If I am applying 1 Tesla or 0.75 Tesla, it is medium grade. If you are applying more than 1 Tesla, this is going to be very hard and depend on your workpiece initial surface. Normally, you can use. The practically how it look like. For example, knee implant is going to be polished where this liquid is placed and electromagnetic field is applied or a magnetic field is applied. When the magnetic field is absent, this is a liquid here on a knee implant. When the magnetic field is applied, you see the droplet which is there on the knee implant jumps and form a flexible magnetic abrasive brush. Okay, can you able to see? This is a flexible magnetic abrasive brush. And again, I'm saying it is like your toothbrush. Only thing is that you are having certain diamond particles or any other particles are present here. Now, depend on the magnetic field here inside. Normally, in this case, we have used the permanent magnet. Once the magnet is activated, what is the thing? It is forming a flexible magnetic brush. In the brushes, for example, toothbrush, how do you choose the toothbrush? For example, in a daily life, I'm asking, how do you choose a toothbrush? Normally, you go to the shop and you normally purchase. So many is still last 5 to 7 years, I also used to do the same thing. But nowadays, people are much educated after this YouTube and other things. How you have to choose the toothbrush is, it should be soft. Nowadays, almost all are soft only. In olden days, I mean to say before 10 years or something, there will be 3 types of brushes. One is hard, one is medium, another one is soft. Nowadays, soft, super soft, and ultra soft came into picture. So this depend on that. How do you decide? Depend on the bristles force that is applying on enamel. It decides the what is the whether it is hard or whatever. So nowadays those hard and medium is slowly nullifying, and you are getting a soft and super soft and ultra soft. Like Colgate sensitive toothbrush will be ultra soft. So that is one area. The second area where we extensively work is that sustainable manufacturing. Sustainable manufacturing means where whenever you do, I don't know whether the video works or not. Yeah, video is not working. So it is saving our time. Okay. So what is the sustainable manufacturing? What we talk about is that whenever there is a machining operation, temperature rises. When the temperature rises, what is happening? So to cool it or to overcome it, what we have to do is you have to take two options. One is going for a hardest tool or which can overcome these temperatures. That means that either you have to go for CBN tool or a diamond tool. Second option, which is not an economic option as per economic countries or developing nation is concerned. For example, the second option is cutting fluids. Cutting fluids ranges from 1200 to 1800 or 2000 per 20 liters. Each liter of this cutting fluid can be mixed with 10 liters of water. In the circumstances, it will go to 220 liters. So 220 liters you are getting for an average price of 1500 rupees. That means that less than a cutting tool. Okay. That means that being an economic country or developing nation, we try to go for cutting fluids. When you go for a cutting fluids, what will happen? These cutting fluids are mineral oil based. Whenever you use in a machining condition, what it is going to do is, it is going to emit a lot of emissions. If you see the example of Kesh Kanti hair oil advertisement, there they will show that oils are carcinogenic. So what oils? Mineral oils are carcinogenic. What are mineral oils? Mineral oils are the petroleum-based products. So most of the oils are mineral oils and these are carcinogenic. And these not only carcinogenic, it also causes a lot of problems like it falls on a face, it falls on a hand, it falls on, you breathe the fumes with the, I mean to say emissions and other things. These are all causes lot of problems like chlorinac, dermatitis, and many other things. So other area where we work on sustainable things is biomicromachining. Biomicromachining stands for machining using bioorganisms. And I am very grateful for IIT Madras for choosing this particular paper as a best paper award. First position, in fact, there are first, second, and third positions. We got the first position. What is the technology here is that we are going to use acidothioBacillus feraccidens, which are microorganisms. Okay, so we try to take from a reliable source, which are certified source, then we try to culture it, then we need to populate it basically. So once you populate it, you need to simultaneously make a sample. For example, in this case, we have two samples. One is micro needle, micro nozzle. Another one is micro mixture. Okay, these are the two things that we have done for which CAD model and other things. Photolithography can be done. First, you need to coat it, and photolithography is done, and so that you need to expose the area where you need a biomicromachining operations. Once you do it, you have to place in the culture medium, and then what will happen? It eats away the surface, and you can see the beautifully how the surface is taken away by or eaten away by the microorganisms. The additional advantage where these particles are going, these particles are can be generated as nanoparticles. So additional benefit, you are getting one side microchannels which are not disturbed metallurgically, and second thing, you're also getting nanoparticles. This whatever the material that we are using is a copper, so whatever we are getting is copper nanoparticles. These are, if you want to go for a purest form of these particles are so expensive, and you can get it from the biology. So it has a two advantages. There is no, if you see blanking and punching, in that case one is waste for us. So here there is nothing like a waste or something. It is, everything is useful for us. Only thing, there will be minimal wastage. We also work into the bulletproof materials. Exclusively we work on Indian Army, whatever they are using. So this is a lightweight bulletproof material that made up of so many materials and so many layers of microns thickness. And we have approximately 6 sections, out of which I can say 3. So first section is to reduce or increase the curvature, or I mean to say blunt the bullet. Second is to reduce the velocity. Third is to give the cushioning effect for the army person or any other person who is wearing it. So these are the 3 most important layers in the bulletproof material, because cushioning is also plays a major role, because sometimes there is no injury, but however the people are dying because there is no cushioning effect and other things. So second area, the same guy is continuing PhD. He is Lieutenant Colonel Sanjeev Kumar Sahu, currently working at Jammu Kashmir. So they have their own facilities, and we only just support partially. So our role will be very minimal here. However, since our inputs are always well taken, this is a project that we are doing with IIT Gauhati, because he is my old student. So what we do is, this is for ballistic impact test for vehicles, because people are transported from one place to another place. So there will be a firing from the opposition and other things. So for this purpose, we are developing a ceramic composites. As you said, we also work on to the additive manufacturing processes. But most important thing is that one has to wisely think, as per today's concern, is that where to use, where strategically one has to use. Okay. So original design, if you see the original design of this antenna, if you see here antenna, so this is 1.6 single pieces we need to join completely. In that circumstances, weight goes to 1.6. Even each and every gram in a satellite does matter. So you can do the topological optimization of this particular thing regarding the functionalization is concerned, and you can 3D print it. The cost may be approximately same, but the weight reduction, if you see, approximately 660 grams is weight reduction is done. That is what is most important. Money is not a matter in some circumstances. At IIT Tirupati, along with our collaborators, we work into many areas of additive manufacturing, ranging from direct metal deposition or direct energy deposition, wire arc additive manufacturing, or there is another one concept called tandem wire arc additive manufacturing, where we do functionally graded materials, powder bed fusion technologies, and many other technologies. We are repairing, laser cladding, you have seen already. This type of things we are going to use. So laser cladding, you can clearly see here, once we do the cladding process. So primarily we do the cladding here. Laser cladding system is when we understand the surface morphology, and most importantly, what we will miss as a mechanical engineer is surface metallurgy. You can see elemental mapping is done, how the coated material, for example, here, if you can see here, this is a transition layer, and this is a coated layer. This is the coated layer. I don't know whether if we able to see or not. Okay, this is the parent material. Parent material is a titanium alloy, and you can see here calcium, red particles are calcium. You can see, I don't know whether how many of you can able to see, and pink one is phosphate. So on top of it, you have red and pink. That means that calcium and phosphate, whatever we have coated is a biomaterials are coated on top of it. Okay. Once you coat, you also should know that clearly what type of surface you are going to get. Suppose in this case, needle type of structures for some input parameters. For some input parameters, you are going to get a circular porosity. Some input parameters you are going to get very less porosity. Why you require a porosity? That is called scaffolding technologies. Scaffolding, because you people are from Kerala, so you should know in a much better way, because Sri Chitra Tirunal Institute is one of the famous institute in India. So where they are expertise in the area of scaffolding and other things. The scaffolding is much required for cell culture applications, implant applications, and other applications, because the cells has to grow properly. And if at all you want to grow a plant, roots has to go inside the mother earth. That is most important. Okay, so for that, the roots and other things has to go inside for the firm bonding abilities. That's why you require porous nature, and you can see the cell density for unit area and other things. Okay, so we also do on laser texturing, because laser texturing is most important for especially titanium implants and other things, because whenever you try to do the laser texturing, titanium is a highly reactive material, because of which what will happen, titanium oxide will form, and titanium oxide is a biocompatible partially. And if you want to coat a partially or a good biomaterials, you can use titanium oxide as a binder for hydroxyapatite or bio-nanoglass or something. Then you can coat. For everything, you need to do lot of characterization in terms of SEM analysis to know how the texturing is done. And once the texturing is done, how the microstructure is there, how the metallurgically structure is there, and the 3D surface profiles, how it is going to do. So most important, and the other important thing that we have to do is, we have done already, but the slide is not there, is contact angle measurement. Once you make a contact angle measurement, what you can do is, you can make the whether the surface is hydrophilic, hydrophobic, superhydrophobic, or none of the above. So like that you can do. Once you do all these things, then you have to go for in vitro biological characterization. So that is called stimulated body fluid studies. Okay, what you are going to do is, you are going to place this particular coated surface textured, on top of it coated, and tribological aspect has to be understood. Once the tribological aspect has to be understood, okay, so you need to go for biological understanding. You can clearly see, you may be looking at the background black, but it is not originally black. This surface is so shiny, that's why the background is becoming black. Okay, so the hydroxyapatite coating, this is the coating region, and whatever the flower like structures that you are seeing is apatite layer. That means that this material is biocompatible. How you can say biocompatible? It is exchanging the proteins, it is exchanging the minerals and other things. So once you do this, then you have to go for cell culture studies. So cell culture studies, you have to understand, and you have to characterize using the fluorescence microscopy. Mechanical engineers mostly, you how and why you require fluorescence microscopy. The fluorescence microscopy is useful in multiple ways. First, to understand how the cells are growing or not. Second, any foreign growths are there, like fungi, bacteria, and other things. And the third and most important thing is that one has to understand how many number of cells are growing per unit area. That means that cell density. These are the three things for which normally what we do is we get for a required cell lines. The required cell lines means, for example, in this case, it is osteoblast cells for the bone applications. MG63 cells are procured and it is are grown on top of the bioceramic coated surfaces, functionally graded bioceramic coated surfaces. Then afterwards, what we have done is we have characterized using fluorescence microscopy. Before characterization, you have to give two dyes, that means colors. One is green, another one is red is given, so that the green is occupying the actin filament and the red one is occupying the nucleus, basically. So the basic problem here is that you are going to coat on a titanium implant, and the titanium implant is not biodegradable. So for example, a common man got an accident and it goes to hospital. What is happening? He assumed that he is undergo a 1 lakh rupee operation. After 1 year, he need to take out those things because it is not a biodegradable. That means that secondary operation is required, where it will cost approximately 0.5 to 0.6 times. That means that 50 to 60% of the original cost will take place. That means the total expenditure that is going to put for that particular operation is 1.6 lakhs. So how to overcome those things that we have understood? So how to reduce the secondary operation, for which we have developed the biodegradable polymers. In the case of biodegradable polymers, we have developed multiple polymers like PLA and PEG. Let me explain about PLA. PLA we are going to do in two means. One is developing the lactic acid monomers, or you can also do by purifying the commercially available PLA. That means you take the PLA and try to take the metal oxides and other things. What are the purity? Once you make it all these things, you have the monomer or a polymer. You can monomer, if you are having, you can do the polymerization or in situ polymerization you can do, and then you can make your own strands. For example, for 3D printer, if you require, you can make your own strands, depend on your compositions, or you can make your own disc for many applications. What we have done is, we have done for the polymers which are blended by hydroxyapatite and other things. Hydroxyapatite is also purified, purely manufactured at our site and the laboratory, and we have used. And polylactic acid also, it is completely indigenous. That's why we have patented this particular technology. And the implants, you can see, if your composition is there, you can play with your molecular weight and other things. For example, for a patient, we want the degradation after 3 months, because after 1 month, what will happen is he is ready for rehabilitation and he is ready for it might have been cured, or it might be completed his functionality and other things. For an elderly patient, it will take a lot of time, means double the time of a young patient. So in that circumstances, what will happen? You need to play with the molecular weight of the weight so that the degradation controlling can be easily controlled. So what we have done here in this particular technology is there, we have done internal fixation devices like cortical screws, canceller screws, as 10-man pins, plates, staples, and other things. You can see the applications of those things adjacent to those things in schematic ways. Okay, how the 10-man pin is going to use and other things. So other technology, what is the advantage of this particular technology? The advantage of this particular technology is you don't require a secondary operation because this will degrade inside. Polylactic acid degrades to lactic acid, which is useful for the body. Second thing, hydroxyapatite is the calcium 1 phosphate. Both degradation into calcium 1 phosphate is also useful for the people for the bone growth and other things. Everything is useful, so there is no problem of degradation inside the body. The advantage here is that you don't require secondary operation. That means one can save the secondary operation cost, that is 60,000. That the common man burden has been reduced from 1.6 lakhs to 1 lakh. Now, can we reduce still further? Yes. The question is, for some cases we can do. So those are the some cases whenever there is a fracture, hairline fractures or some low load applications. Okay, some low load applications for hand and finger applications, if you see the surfaces are very, very rough. In fact, 3D printing cannot do those type of complex features. So what we have done is we have developed the injectable, thermosensitive injectable magnetic scaffold, which is a liquid at room temperature of 22 degrees to 25 degrees. Once we inject into the site, what will happen? It is 37 degrees of human body. It is goes and occupies nooks and corner of this one, because we are going to study about the tribology. We are going to study completely of the rheological study, so that its flow as well as deformation and the tribological, because of the micro vibrations, nano vibrations, and other things. These are, and once it reaches to 37 degrees, what it will do, it becomes a porous solid. Once it becomes a porous solid, then what will happen? Bone is an autotomy. It can grow from both sides and it will collapses once the growth is proper. So the advantage here is you don't require 1 lakh. Why? Where is the 1 lakh is going? 1 lakh is going for pre-operation testing, post-operation rehabilitation. You have to stay for 3-4 days. Okay. So, and operation theater cost, surgeon cost, and these are the major things, not the implants or internal fixation. Internal fixation, implants, whatever you have seen in the previous slides, they may cost you 2,000 to 5,000 to maximum 10,000 rupees. Okay. So in fact, if you take on a positive side, your expenditure is not going to take place more than 25,000 to 30,000. That means that whenever we try to do the research, what is the motive should be that you should able to help the common man. In fact, you should able to help a poor person. If you are going to help a below poverty person, that means that you are a good person and you are doing your research in a right direction. That is what I can say. Once we have the knowledge about this polymer matrix and the polymer nanomatrix and other things, because nanoparticles and other things, we also have the technology about the cells culture and this are in this matrices and other things. And we are now venturing into the another area called 3D bioprinting technologies. 3D bioprinting we are not using for the ear and other things. We are only concentrating at this particular moment for skin application and other things, because it is slightly easier compared to the organs printing and other things. Okay. Do we really require micro nano finishing? Yes. If you see the micro nano finishing, if you can see the second image, so nano finishing is at most important in terms of using for biomedical applications and other things. Okay. These are the biomedical applications where one has to polish. So how to make a smart system for this polishing of biomedical implants? Because polishing of these things manually is very, very dangerous. Because why? Today he may be happy, he will do the polishing with good patience. Assume that tomorrow he has a quarrel with his wife at home, gone. Whatever the anger is having on his wife, will show on the implant. So that's what. So that's why automation comes, and now smart manufacturing, everything has to be smart now. So how these are doing currently in Indian scenario? First and foremost thing is vibratory ball finishing process. Vibratory ball finishing process is just you dump all the implants and you rotate it. Basically, what is the problem here is, the problems here are multiple. For example, if you take this as an axis, if you have an implant here, it will rotate only this much distance. If you have an implant on the surface, it rotate about this much axis. So there will be a non-uniform surface roughness on the components. For example, these components are fragile. What will happen? This may collide each other, because of which what will happen? This may fracture and other things. To overcome this, Indian industry, they are coming to another technology called drag finishing. Can you able to see the video? Clearly watch the video so that you will understand, where you can have one implant at one location. By the one holder will have 5 to 6, but their position is fixed, so that implant won't impact each other. That is the only advantage. And at the same time, uniform finishing slightly you can achieve, but it is a global spectrum, but it is not a local spectrum. Means micro nano location. You can see the zoom version here. So the rotational speed and other, you can see here, the implants are now slowly coming up. Knee implants are slowly coming up. This particular facility we have recently started procuring and other things. Okay.
So what is there at the bottom, sir? It is abrasive particle or sand?
What? Can you repeat the question?
What is there at the bottom? It is abrasive particles or sand?
Abrasive particles. So those abrasive particles are slightly different from normal abrasive particles. Those abrasive particles are slightly bigger. It looks like a cone. It look like a, so many abrasive particles are there. Even some chemical also will be, you can see from the side, there is a chemical is another coming. So these abrasive particles are big. Okay. These are called as abrasive beads basically. Okay. So this is for mass finishing applications or batch finishing applications. Another thing people normally uses in Indian scenario is robotic grinding. Robotic grinding, you can see for hip implant, how the hip implant is going to be finished. Not viable for nano finishing, because you may get a good surface finish up to 500 nanometers or 600 nanometers. For example, if you still want to go below it, then it will be a problem. Okay. So that is the where the people are going towards liquid based cutting tools or semi-solid based cutting tools. Because if you hit with a tennis ball, if you are going to hit with a stone, where you will get impact more? With a stone you will impact. Assume that the velocity is same, assuming the size is same. In the circumstances, what will happen? Your stone will impact a lot. When your stone is impacting a lot, what will happen? The indentation depth will be high. Indentation depth will be high means the roughness that you are going to achieve is not up to the mark. That is what the technology. That's why we are moving towards liquid based technologies. Okay. So the drawback here is that all solid tools interaction forces are very high. That's why in the present study, what we are going to use is, we are going to use a polymer based finishing technologies where high viscous, medium viscous and low viscous fluids are developed, and we have patented these technologies and other things. This is the smart machine. How we made it smart, we'll see in the last few slides. First, we have to understand about the machine, then only we can make it smart. So this is a structure. This structure has a fixtures and most importantly, medium and other things. How the medium works and other things is may not be a thing here importance. Now you can see here how the medium is going to work. Medium is going to work for a viscoelastic medium. So viscoelastic medium works on a viscoelastic principle, because this particular slide almost took us 2 to 3 years of our PhD life. Okay, this looks very simple, but we used to try to different polymers, but those are not giving a good surface finish into nano. For example, 10 nano, 20 nano and other things. We are regularly getting 100 nano, 200 nano, 300 nano and other things. But whenever we want it to a 10 nano or below 50 nano or below 100 nanometers, it is very rare case that we are getting it. In that circumstances, what is the thing is, we went on to one of the science understanding that is called viscoelasticity or viscous and elastic component. For example, here I will just explain you. You take a viscoelastic polymer which is supporting the abrasive polymers. Green ones are inactive abrasive particles and blue ones are active abrasive particles. Active abrasive particles means which are in contact with your workpiece. Now you are taking a element of viscoelasticity and you are applying a shear force. It has a viscous component, it has a elastic component. Viscous component tries to move along the direction of application. Elastic component move perpendicular to it. Now the question is why and how. So you take a viscous fluid like honey and just take into your hand and try to throw in one direction. Throw means just you push. What will happen? It tries to move in the direction of push. That is because of viscous nature. For example, if you take an eraser, you have kids, many people have kids. You take a pencil eraser, which is elastic dominating viscoelastic medium. So rubber is not a pure, or eraser is not a pure elastic one. It is a elastic dominating viscoelastic one. Whenever you try to press it, what will happen? It try to move in perpendicular direction. That everybody knows. So now that is called radial force. Now you can see the analogy of this one. What is analogy? You have an abrasive particle here and you have viscoelastic medium. I am pushing by hydraulic power pack in this direction. What will happen? Axial force move in this direction and radial force move in this direction, and you have axial velocity also. So because of which, what will happen? This will try to shear off the surface peaks. That is the basic science. Once you understand the science, then you have to go for the medium. So the medium is a bit complicated. It is flows like a fluid, it behaves like an elastic ball, it behaves like a plastic piece also. Flows like a fluid means whenever you make a spherical ball and put on a flat surface, what will happen? It will become a flat at the bottom. Second thing, it behaves like an elastic ball. It is becoming a flat on surface. That means that it is, do you think it is sticking? No. If you just try to lift up, it will come. So what is happening is, if you make a spherical ball again, try to hit onto the ground, what will happen? It will jump like an elastic ball. Okay, so that is what it happens. The third end, it breaks like a plastic piece. Means you just take a medium into your hand and try to pull. What will happen? It will just make into pieces actually. So what do you understand from these statements? What do you understand from these statements is the flow behavior, the deformation behavior are completely unique. So one has to study the science of flow and deformation. That is nothing but the rheology. Rheology is nothing but the science of flow and deformation. So we have studied multiple rheological. However, for small glimpse, we are going to give you few experiments that is called steady state rheology, where we are going to explain you the flow properties and creep compliance or creep recovery And dynamic, we are going to give you frequency sweep and amplitude sweep. Currently, we are going to give amplitude sweep only. The schematic diagram look like this. This is the bottom plate, which is fixed bottom plate. And this is a rotatable top plate, which is also called as a tool master. And in between, you have a medium, ash color medium. Okay. Now, experimentally, you can see here, this is the top plate, how it look like. This is the top plate, and this is the bottom plate. And in between, you have a medium. So how the medium look like is this. Okay. So what you are going to experience now, you see the signs of understanding of this steady state rheology. As I am increasing the shear rate, so x-axis, you take any one curve because all the curves are following the same trend. What is happening here? So region 1 is there, region 2, we have divided into region 2. As you are increasing the shear rate, that means the tool master, which is the top plate, slowly increasing its velocity of rotation. What will happen? Polymer molecular chains are like this and slowly climbs one over each other. That means that the resistance offered by the polymer molecular chains will gradually increase. That means that there will be a sensor, actually, torque sensor will be there, which is also there will be air bearing and other things. So it gradually increases. Beyond which, what will happen? It start breaking. Polymer chains has its own strength, beyond which it start breaking and align in the direction of the motion. That's why the shear stress is decreasing. Now we will see the another area where in this curve only, across this, if you take green one is on the top, pink one is at the bottom. That means that 7.5 to 12.5, the shear stress is decreasing. Why the shear stress is decreasing? Just we will see. I have a polymer molecular chains. These polymer molecular chains are nearby. That means that cohesive strength is very high. Interpolymer molecular distance is low. That means that force of attraction between two polymer molecular chains is very high. As you impart the plasticizers are low molecular weight materials. However, polymers are high molecular weight materials. Whenever low molecular weight materials are blended with high molecular weight materials, low molecular weight materials try to go and sit in between and try to kick apart. So what will happen? Gradually, the distance between two polymer molecular chains is increasing. That means your force of attraction between two polymer molecular chains is going to decrease. Still, if you are going to increase, what will happen? Your force of attraction or cohesiveness is going to reduce. That means the force of attraction between two polymer molecular chains is going to reduce. What is the bottom line of the story? The bottom line of the story says, I have an elastic dominating material, or I have a viscoelastic material where dominating elastic characteristics are there. Now I am increasing the viscous component by blending the viscous dominating mediums. Now the second test, normally what one has to do is creep recovery test. Why you require creep recovery test? I was telling that this medium is a viscoelastic medium, this medium is a viscoelastic medium, and other things. Now, this is a viscoelastic medium. One should know always how much viscous is there, how much elastic is there, because you are imparting the viscous component. So now, if you are imparting, you should be able to characterize the same also. Okay, that's why you need to do. So now, how do the creep compliance test or creep recovery test? Creep recovery test done by suddenly apply certain load at A. You are going to apply a load and you are holding for certain time and releasing. Now the $1 million question to ask is, how much load I have to apply? For which one has to do dynamic rheology, that is called amplitude sweep. Now we will go to this curve once we see a small curve at the bottom. Now you see here, I am changing the shear stress, which is nothing but our load, whatever, our stress. Okay, units are different, but so stress I am changing and I am observing the storage modulus. Storage modulus means the absorbing ability by the polymer molecular chains. There is no change in the storage modulus up to certain extent, beyond which there is a change. That means this region is called linear viscoelastic range. That means that even though I am changing the load or a stress, whatever may be, there is no change in the storage modulus. What it mean? It means that my polymer molecular chains are not disturbed, not broken. Only thing is that it is absorbing the energy without any failure, beyond which it is failing. So if I can take any particular value in this region, linear viscoelastic region, and I can put into this test, what I'm going to do, what I'm going to get is my polymer molecular chains are at original strength and those are all not disturbed or not broken. So I am going to get the realistic value of viscoelasticity and viscous component as well as elastic component. That's why we have chosen a value called 100 Pascal and we are going to give 100 Pascal here at the A and holding the for the creep complaints. As you know, the complaints, reverse of modulus and other things. Once you understand this, A to B is your viscoelasticity and B to C is elastic recovery. After that, okay, there is no elastic recovery. Now we have viscous plus elastic and elastic. From there, we can measure what is viscous component and other things. Once you understand all the signs, if you see here, if my viscous component is 35%, my elastic component is 65 because both are 100%. If my elastic component is dominating, you can see here, if my elastic component is dominating, radial force will be high. It is not only shearing the surface, it is also create its own scratch marks. That's why one has to go and optimize the medium such a way that you should have proper elastic and viscous components. Once you understand the science, these are all applications you can do. Once you have wheat flour, we used to have one professor, Professor Rajendra. He used to tell us, if you have wheat flour, you can make chapati, puri, dosa, whatever you want. Okay, like that. Once you have the science and technology in your hand, patented technology, and you patent it, you can use for any type of applications. For example, in this case, we have used for knee implant application for polishing and other things. You can clearly see how polishing plays a major role in terms of biomanufacturing and other things. So it can be extended for hip implants, acetabular heads, heart valves, and other things. Second, these are high viscous mediums that we have seen. Now we are going to see the low viscous mediums for heart applications and other things. I'm not going to touch about micromachining. Just I would like to give you a glimpse. Whenever you do laser micromachining and other things, a recast layer. The recast layer is very dangerous. Okay, so this recast layer is very dangerous because this is a molten material resolidified, which is not part of a parent material. Whenever you are going to use for some of the drug eluting applications for point care technologies, it is very dangerous because this will have a metallurgical change or it will change the drug compositions. Second, it will also have can come along with the drug and try to kill the patient. So that's why one has to be bit careful about this. Okay, so these are the one. What is the thing is our medium has flexibility. So we have patented the technology. If somebody purchases our medium, it has high viscous or medium viscous. If you purchase, our setups as completely controlled by the temperature controlling unit, because you will see some of the images of our systems, what we have developed. These are the smart systems. Temperature controlling unit is there, force controlling unit is there, and all controlling sensors are there actually. So assume that application is for low size applications or micro applications. You need to have low viscous medium, for which our temperature controls or temperature sensors, if you intact, if you can give the signals, or you can give on the HMI, that is called human machine interfaces, it will suggest you what are the viscosity that you are talking about. This is the polishing. Initially, the surface preparations and other things, which is of less importance. Once you understand the polishing, you can see here how the polishing has taken place. The recast layer is removed and the parent material is achieved. This test is done on SS316L for the initial studies. And then we proposed for initial trials. We have done up to 50% of the work and we have presented for BIRAC, and BIRAC kindly accept our the things, and they gave us about 40 lakhs of funding for testing for drug eluting stents. So we also do for fuel injector nozzles and other things. Okay, so these are the main components. Now we will move to how we have converted into a smart, just a glimpse. So first and foremost thing is that you need to design your system, what you require. Once you understand the physics of the process and other things, then you have to go and design your system as per the motion sequence and other things. So these are the multiple designs which we have done, and the final design is design 4, whatever you can see here. Once you fix your design, now you know what are the motions that you want, where and how to control. For example, whether you want to control by pneumatic, whether you want to control by hydraulic or something, linear slides and reciprocating slides. At the same time, what you need to do is how you should come out of the patents, because in this area already 5 to 10 patents are there. How to come out? So in what terms we should have the patented technology, so for which you should do a lot of work. I cannot explain much things because this patent is applied recently, because we have already 2-3 patents in this area, but this is a smart one. So how you build it, because you see the electronics, you see the base structures and other things, how we are going to build it. Once you build it, now you need to control by the electronics. You should understand the electronics. At the same time, what is the thing that you want? What is thing you want is we have to move the medium across the surface to be polished, for which how you are going to move, how we are going to move is through the hydraulic power pack. Now one has to understand the intricacies or internal circuits of a hydraulic power pack, which is given here, and you have to draw your own internal circuit, and you have to control your solenoid valves, limit switches and other things. Once you have done that, you should make a HMI, which is electronics embedded systems, which I don't have much rights to explain in a greater way. We have one HMI that is called human machine interfacing, that you can see in the upcoming slides, where you give the instructions. For example, I want 50 number of cycles, extrusion pressure is 6 megapascal and other things. Then programmable automatic PAC will be there, which can convert analog input and analog output into digital input, digital output. Then it will give to the, through the DCV, it will give to the hydraulic power pack, and it will have the power pack. Also, you should be able to choose such a way that it should have proportional valve and other things, because sometimes load is not there, it is not, it should not go very fast. Sometimes load is there, it should go fast. It should have a proportionally how to move. See, assume that my liquid is moving from one cylinder to another cylinder. In that circumstances, one side it is vacant, another side it is fully filled. So if there is no proportional wall, what will happen? The cylinder or the piston which is there or the empty side may go very fast. That is the basic drawback. So Rome is not built in a day. We started this particular machine in 1996 and 97. We built continuously, improving and other things from 2005, 2006 we have built. Then 2007 and 2008 we have improved the rotational ability and improved the production rate. Then we made a smart machine, which is human interface machine, that you can see here clearly. And this is the completely human machine interface machine. And This is a smart machine that we have fabricated at IIT Tirupati, which can polish simple geometries to the complex geometries. And we are working with so many companies for polishing their implants and components, complex components and other things. I cannot show because of NDA agreements and other things. We have also transferred our technology to some of the leading organizations where the machines are continuously working, and you can see the revenue generation and other thing. This is also one of the technologies. This is not a smart one, but it is slightly automated one where you can see a lot of buttons are there here. Okay, so this is a button controlled one. Our this is a touch screen, completely embedded electronics controlled one. So that is about the technology one. Coming to MOOCs, I have 3 courses. Those people who are interested, they can go and see. At the same time, I'm also editorial board member for IMECI and guest editor for International Journal of Precision Technology. Those people who are working in micro nano manufacturing can submit a good science-oriented publications to our journals. Acknowledgements. Acknowledgements are funding agencies. Basically, funding agencies are those who gives funding for the research, starting from IIT Guwahati about 5 lakhs, Baba Atomic Research Center about 23 lakhs, DST about nearly 1 crore. That is whatever the setup that you have seen is developed in DST project about 1 crore, DRDL about 75 lakhs. Then comes the big budget called 60 crores from DIT, which is called now MIGHTY. So Ministry of Electronics and Information Technology, where we extensively work on biomanufacturing and other things. Imprint about 6 crores with the 2 institutions, IIT Kanpur and IISc Bangalore 3+3, IIT Tirupati about 22.5, SCRB about 45 and BIRAC about 41 nearly. And we have got a big grant of 120 crores for Technology Incubation Hub on Precision Technologies, where I am heading one of the division called Precision Manufacturing. I'm also thankful for all the students ranging from summer interns to the postdoctorals. So I am just a front face. I am doing these people are the backbone for me. I am just showing what our research. So some of there from my research also. So I can say that 30 to 40% is there what I did on hands-on experience. Thank you once again for giving me the opportunity. And if you have any queries, suggestions, I am ready to take up. Thank you.
Thank you, sir. Thank you for the very good presentation. Any queries from the participants?